The exponential distribution for us is going to be the first real distribution that actually has industrial applications that we're going to look at. Its actual accuracy can be debated, and there are certainly also more sophisticated models now. But as a first approximation, actually the exponential distribution is very good to model the time that passes until an event happens, because basically in the introduction we had talked about a situation where there's a parameter theta, so that the probability of an event happening in a short time interval of length t is t over theta. And well, that sort of makes sense if you have events that are happening randomly, that the chance that an interval should capture the event happening should be proportional to the length of the interval. And basically, when that is the case, then we had proved in the introduction that the probability that we have to wait, the waiting time t, that we have to wait for the event longer than lowercase t is e to the negative t over theta, which actually turns out to be the integral from t to infinity 1 over theta e to the negative u over theta du. And so this time, the waiting time until an event happens, is often called the time to failure in industry, and it is obviously a very important design parameter, because companies try to estimate this time to failure from parameters of the manufacturing process, but also through testing of components, burn-in cycles, and so on, because depending on what they expect the time to failure of a component to be, that's how you set your replacement cycles. If you're in an industrial setting where certain things are just routinely replaced because you want to keep the shop going all the time, that is also how you set up your warranties. If you're selling consumer goods, you want to have a device obviously that works well and works well for a long time, but a matter of fact just is that these devices don't work forever, so you want to set a warranty that is obviously long, but at the same time not so long that you've got so many warranty claims that another part of your company is just losing too much money. Okay, so how do we define this thing? Well, we define it exactly the way we've just seen on the previous panel. The exponential distribution with parameter theta greater than 0 has the probability density function f theta of t, so it depends on that theta, and it's 1 over theta e to the negative t over theta for t greater or equal than 0, and it is 0 otherwise. So the actual analysis as to what kinds of waiting time phenomena the exponential distribution fits well, that goes into a probabilistic analysis that is beyond the scope of our first introduction here. But as I said, there are certain phenomena for which it works fairly well, and it's often also a pretty good first approximation. Okay, a quick word of warning: the exponential distribution is also sometimes written with a parameter lambda equals 1 over theta, and that would then mean that the exponential distribution is also written as f lambda of t, being lambda e to the negative lambda t for t greater or equal than 0 and 0 otherwise. For the purposes of our presentations, we're going to stay with the formulation where we've got theta as a parameter, and as we're computing the mean, we're going to see as to why that may be a little advantageous to actually have a parameter in the denominator. The only other thing to say here is then, similar to what I've mentioned in the introduction for the probability functions, basically the parameter theta certainly changes the shape of the exponential distribution a bit, and then we've got a 1 over theta out front that just makes sure that the overall integral of the distribution actually is equal to 1. Okay, so let's just take a look at some examples, because the interesting thing ultimately with these probability distributions is that if you understand how the probability distribution works, how it applies, and if you can do the computations, you can do an awful lot of good statistics without worrying too much about the actual shape of the functions. So our examples will be waiting times here, and so let's take a look at something where a certain download starts in a waiting time, or you have a certain time to wait until the download starts, And that waiting time we assume is exponentially distributed with theta being 2 seconds. Well, then we want to know what the probability is that the download will start before 5 seconds have passed. Well, we have that theta is equal to 2, and that's pretty much all we need to know, because now the probability that the download starts before 5 seconds have passed, that means that my waiting time t is smaller than 5, and so that's the integral from 0 to 5 of my density function, which is 1/2 e to the negative t over 2, where theta equals 2 comes in here as well as here, right? And now we just find our antiderivative. That's a quick u substitution, and the antiderivative ends up being negative e to the negative t over 2, and we have that in the boundaries from 0 to 5. And so that gives us negative e to the negative 5/2 at the upper bound minus negative 1 at the lower bound, which is 1 minus e to the negative 5/2. And then if you have a calculator available, you realize that's about 0.9179. It's about 92%. And well, so that is something that for waiting times after you're seeing how exponential distributions work, that's actually a pretty reasonable number. If you have a parameter theta of 2 seconds, that then by the time you double the parameter, that you've got a very high likelihood that things will already have happened. Basically, even if you don't draw it to scale, you realize here that for an exponential distribution, most of the area happens early, and the tails typically have very little area, even if we don't draw the area to scale here. That is roughly what happened on the previous panel. Okay, well, this is a situation, well, obviously all of the examples that I have here are made up, but this is the situation where you know the theta already, and of course a lot of probability and statistics is also just set up to determine what the theta is. So how do you determine this theta? Well, consider the following. Take a look at my friend Dr. Absent-Minded, and the time until he gets a stomach ache after eating a pound of chocolate is exponentially distributed. Okay, so we're assuming that that's a waiting time distribution. And long-term experimentation has shown that there is a 90% chance of discomfort within the first hour of eating a pound of chocolate. Things that I do for science are just amazing. And so now we want to know what are the good doctor's chances of being okay for at least a half an hour. Alright, so that is not something that I would recommend to do. Long-term experimentation can certainly lead to damage and things like that, so it's obviously a made-up problem, but some of this certainly is real, because if you have a good reason to assume that your process is exponentially distributed, then if you just run enough experiments, you can estimate a certain probability. Here, there's 90% probability that something happens within the first hour, and from that probability you can infer what the underlying parameter is, and once you've got the underlying parameter, you will be able to compute other probabilities. So this is now something, even though it is couched in something that is deliberately even sounding like it's made up, it is a fairly realistic process. You measure a probability, you estimate a probability, you get the parameter, and once you've got the parameter, you compute another probability. So what do we have here? We have an exponential distribution. We have that up to 1 hour, the area up to that area is supposed to be 90%, which is 0.9. Again, I had just one generic picture, and I just changed the numbers in it, so it's not to scale. But even a generic picture tells us, yeah, we are interested in the area to the left of 1. We're interested in the area that is early, not the area that is late, and that's pretty much all we need in order to set up the problem, because that tells us that we have to take the integral from 0 to 1 of a generic exponential distribution, and we have to set that equal to 0.9, because that's what that area is supposed to be. So if we do that, we take a generic exponential distribution, integrate it from 0 to 1, and we get, well, the antiderivative is negative e to the negative t over theta. That's a quick u substitution, or you could just take a look at this thing, differentiate it, and verify that this really is the antiderivative of this integrand. And we have to take this negative e to the negative t over theta from 0 to 1, because those are our bounds. And we want to set that equal to 0.9, because we want that this probability is equal to 0.9. Okay, So when we plug things in, that tells us that at the upper bound we have negative e to the negative 1 over theta minus negative 1 at the lower bound, and that's supposed to be equal to 0.9. And now we just solve an equation, right? So I think I first simplify the negative signs here. Yeah, that's 1 minus e to the negative 1 over theta. That's supposed to be 0.9. Now we bring over the 1, we subtract the 1 and deal with the negative signs. So we get negative e to the negative 1 over theta is negative 0.9, negative 0.1. And then we cancel the negative signs also. And now we have to solve an exponential equation. Well, we had to solve an exponential equation overall right away. How do you do that? You first isolate the exponential, then you take logarithms. And so taking logarithms on both sides tells us that negative 1 over theta is equal to ln of 0.1. And that tells us that theta, as we multiply by theta and divide by ln 0.1, we get that theta is negative 1 over ln 0.1. And that's about 0.4343 if you want to have digits. But of course, what you also want to do is, as we have a follow-up computation, you want to use the exact value. You want to use the negative 1 over ln 0.1 in the computation itself, because that way you're avoiding early rounding errors. Okay, so this is half the problem, right? We now know what the theta is. Now we can actually figure out the probability that we're interested in here. And the probability is that the doctor will be okay for at least a half an hour. Okay, so that means we've got this waiting time distribution. Here's a half hour, and when we say you're okay for at least half an hour, does that mean stuff happens before or after 1/2? Well, at least half hour being okay, that means that the waiting time is longer than 1/2. So that means we're interested in this area here. And again, the area is not necessarily to scale, but the generic picture tells us we're this time interested in the area under this tail here. And so that means with theta being negative 1 over ln 0.1, we're interested in the probability that the waiting time is greater than 1/2, which is the integral from 1/2 to infinity of, and now because of the 1 overs and everything, we actually get negative ln 0.1 is 1 over theta, and negative 1 over theta is actually just ln 0.1 without the extra negative sign times t dt. And now we integrate that, so the substitution would be u equals ln 0.1 times t, and as you work out that u substitution, your antiderivative is negative e to the ln 0.1 times t from 1/2 to infinity. And that gives us, of course, at the upper bound, because ln 0.1 is a negative number, right? Just because we don't have an explicit negative sign here doesn't mean that the exponent isn't negative. ln 0.1 is negative 0.4343, I think, or whatever the decimals were in the previous panel. And so as t goes to infinity, this exponential still goes to 0. And at the lower bound, we have negative e to the ln 0.1 times 1/2, so ln 0.1 divided by 2, so that's e to the ln 0.1 over 2, and if you simplify that, e to the ln 0.1 to the 1/2 is 0.1 to the 1/2. So that's square root of 0.1, and I don't know how to simplify that, or I don't see it very quickly, so certainly without any further acrobatics, you could have used a calculator right away. Your probability turns out to be about 31.6%. And, well, that's already the end of our presentation here for the exponential distribution. You now have seen the two ways in which we're going to solve a lot of problems that involve probability. On one hand, it could just be that all parameters are given and we just need to find a probability, but it could also be that we somehow, through processes that you would learn about in more advanced statistics classes, we would know that the underlying distribution is a certain type of distribution, and we use a certain measured or estimated probability in order to find first what the parameters are, parameters are, and then we determine a probability that we're interested in. All right, well, you probably have to do some homework problems on exponential distributions, or you may want to watch the presentation on normal distributions. I'm going to do what my buddy's doing. I'm going to eat some chocolate.